Hi, my name is Kushal. I'm a learning assistant for Physics 5AL, and this is.
I'm James. I'm a third year biochem major, and I haven't started the physics series, so
Have you ever taken any physics in your life?
no, I haven't even taken it in high school.
Okay.
So this is all new to me.
Awesome. So let's start from the basics then.
Alright.
So there are three fundamental quantities in physics that we need to be aware of to be able to describe the free fall of an object.
Okay.
So they are position, velocity, and acceleration. So what do you think position is?
The orientation of the object.
Orientation of an object? So
Where the object is, the height of the object, where the object is in space.
where the object is in space.
Okay, yeah.
That's, yeah,
Sure.
so, because with orientation, like right now I'm oriented towards you, but I
Right.
could be here,
Right, and you
but my position is the same, yeah.
Yeah.
So it's,
So your position is a certain coordinate
mm-hmm.
in space.
Right, so
Sure.
in space, but there is another key important thing here. So say my position is, like I'm at some point right now and I walk 2 steps ahead. How
Sure.
far am I from that point? Like
Two steps.
2 steps, right? Say I'm in New York and I walk 2 steps away from that point. How far am I?
Two
from
steps from New York.
Yeah, so I'm in New York, but I take 2 steps over there. So how far am I from that point in New York?
2 steps.
So in both these situations, I'm 2 steps away from a certain.
Sounds very vectory.
I guess it is. In both these situations, I'm like 2 steps away from this thing, but they're fundamentally different things because I'm at different positions. So what is different with those things?
Your location.
Yeah, true. But more like 2 steps. Like say my position is 2 steps, right? What am I missing? Like if I just tell you, hey James, I'm like 15 minutes away.
So forward, backward, to the
Yeah.
left, to the right.
But okay, say I'm like at pizza. No, I'm sorry, I'm at In-N-Out, and I say, James, I'm 15 minutes away. But what am I missing in that information? What if a third
15
person
minutes
was
away from where?
right? So the
Sure.
the other distance is what we need. So position is basically where you are, which is what you said.
In relation to a certain spot.
Perfect. Where you are
Sure.
with
yeah.
respect to a certain arbitrary point. So it's arbitrary because you can pick this point, you can
Sure.
make it wherever. Like I'm 15 minutes away from James, I'm 15 minutes away from
Right.
Young Hall or whatever. So like where you are is with respect to this.
Mm-hmm.
What do you know about velocity?
Well, back in my Math 32A days,
Mhm.
we did that. So you have, it's just how fast something is going.
Mm-hmm. So for the case of free fall of an object, we'll just assume everything's one dimension.
Mm-hmm.
So don't be like scared about vectors and stuff. It's just the y-axis really.
Right.
So what that essentially does is makes velocity and speed the same thing.
Right.
So if I were trying to explain what velocity is in terms of position, how would I do that?
So how quickly something is traveling away from a certain position.
Perfect, right? So
How many
that is
units of distance it is going away from that position
yeah, but this
Per-
definition, right?
per unit of time.
Right. So I was just gonna say that this definition is not as good as your other definition. So we can let's use in the terms of positions like
Sure.
change in position.
Per unit of time.
Perfect. Per unit time.
Yeah.
Okay. And how would you define acceleration?
How quickly the velocity is changing, so increasing or decreasing.
Mm-hmm. So change in velocity.
Yeah.
But is it just that?
Well, I guess it's the derivative of velocity.
Mm-hmm. So in this one, we had where you are with respect to an arbitrary point.
Uh-huh.
Here we had change in position per unit time.
Uh-huh.
So if we change in velocity, is
Per
acceleration
unit time per speed or per
I feel like you have some other knowledge coming in because you know that it's second squared. Is that why
Yeah.
you're saying per? So actually that plays out because it's actually still change in velocity per unit time.
Mm-hmm.
So you must be wondering like how's it second square? So well, this is actually another topic that they teach you in physics before this. So it makes sense. Like
Okay.
so velocities change in position per time. So that you could call that meters per second.
Sure. Yeah.
So if you have velocity per unit time, you have meters per second per second. So
right.
the second comes from
the
velocity.
That's
That's why it's second square. All right, so we're already ahead of the curve here.
Never happens to me.
So we have established 3 basic definitions.
Yeah.
All right, so now we're trying to describe what's happening to this ball when I just leave it like this. All right.
Okay.
So
when you leave it in the air, basically.
just leave it in the air so it falls down.
Right.
Okay. So let's say at time equals 0, my ball is here.
Yeah.
At time equals 1, my ball is here. And at time equals 2, my ball is here, which is the ground. Even though this didn't take 2 seconds to fall, it took like more like almost 1 second.
Yeah.
I'm just increasing it so the math works out.
Sure. Yeah.
So now we are trying to describe this in terms of all these quantities we have.
Okay.
So for position, we usually denote it with x. For velocity, we denote it with v. And for acceleration, we denote it with a. So for all these, at these 3 different times, I want you to help me fill in these different quantities.
Sure.
All right, let's see what you know.
X equals, well, I guess it would be easier if I put like a distance right here?
Yeah.
Sure. We can say,
so here is the issue with this, is that you don't know if, like say this is 1, 2, 3, 4, 5. So according to this scale, this has moved 5 units away from this point.
right.
But we don't know if it has moved 5 units because we don't know how fast it's going or anything like that. So we need to start with our core definitions.
Sure.
Because we need to make some assumptions here. So x, what is x?
I guess it's arbitrary.
Yeah, it's arbitrary. So you get to pick what number you want x to be.
Yeah. I'll just say that x is 1.
So you want to pick this as 1.
Sure. Yeah.
1 meter is away from. So what's your arbitrary point that it's 1 meter away from?
Here.
Okay, so if this is 1 meter away from this, when this comes here, would it be? Well, what would this x be then? You can't say that really. You need to know. Oh, actually, you defined it as 1 meter away from this. So what would this be then? So if this is 1 meter away from this, and this is x is equals to 1, what would this be?
2.
Okay, say you're saying that you are, say this is James, just write James there. And this is Kushal. Alright, so you're saying that James is 1 meter away from Kushal. That's what you said over
so
here.
I guess it's -1 or
So-
0.
Right.
0.
Does that make sense to you?
Yeah, because you traveled a meter.
Mm-hmm.
Yeah.
So that point is 0.
Okay.
It's like you're trying to graph it, but
this is, well, I guess it depends, but it's negative how far away. So I'll just say -1, I guess.
Yeah. It depends. So if you pick this to be positive 1, then this has to be -1. But if you said like 1 meter away from here, it's also 1. But then it's basically like flipping the number line either way.
Right.
Yeah. But here is the thing. We don't know. I mean, you just assume that this point is 0, but we don't know if the ball actually reaches this point at 0. So it's like complicated. Like I can just, like when I actually leave this ball, after 1 second, it might be here, it might be here. You just assume that point is 0.
Yeah.
But I said at time 1, this ball is over here. So you don't know if at time 1 it's at 0. You just you instead define this, but then in that case the definition like time
is
is
just
constant.
based on this.
All right,
right?
so
it's based on how far it is from here.
So if you base this on how far it's from here, which is 1, then this has to change because both of them can't. Like we don't know if at time 1 it's 0.
So I guess maybe I can.
Here's yeah.
I guess I can just define this as sigma, and then I can say sigma minus 1.
But the thing is, oh yeah, actually, that works too. That's adding a lot of variable. Let's just like make the simplest assumption possible for like just because we're like starting off.
So I could say this is 0.
Yeah, that would be the simplest assumption. Now, no, hold on.
Oh shoot.
Sorry.
Oh shoot.
Why? Tell me why we couldn't write -1 there.
Because we don't know how far it is.
Yeah, we don't know how far it has reached after 1 second.
Mm-hmm.
So like, when I leave this, like, it's taken some amount of time, and like if I freeze that frame at some time, like if I freeze after 1 second, it might be here. If I freeze after 2 seconds, it might be here. We don't know how fastly it's changing. We only know that this is 0. So let's start from there. We know this is 0. What about velocity?
Well, it's not at this point in time, and if no time has passed, then the velocity is 0.
Yeah.
And therefore the acceleration is 0.
So hold on.
Wait, no, that's not true.
Yeah, but let me explain to you why it's not true. So when I leave this ball, okay, wait. First, tell me why velocity was 0 based on this definition, not because
it has not changed position yet.
Right, it has not changed position. So
correct.
Can I see that?
Sure.
So based on these definitions, we had position, which was 0.
Mm-hmm.
So x is equal to 0. We're using x. We need to find v. So v is equal to change in x over change in time.
Yeah.
But this is 0, so we have whatever here.
0 over.
But a is change in velocity.
So delta
now,
v.
Yeah, so delta v. And what is delta v equal to? What does delta mean?
Change.
Change, right?
Change in velocity.
So change in velocity. What is change in velocity?
The change.
Like, how would you mathematically find change in velocity? No, those are like
fine.
So, like, if
I mean, I guess you could just find the distance traveled and then put it over
I
how
guess
much time it
so
took.
you're going more like in more complex kinematic equations. Say if I said that I am 50 kilos today and I'm 60 kilos tomorrow, how much did my weight change?
10 kilos.
So how did you find that?
Subtract
Mm-hmm.
your end kilos from subtract your starting kilos from your end kilos.
Perfect. So what is delta v? Change in v.
Your change in your initial v, or change in your end v.
Is it my initial v?
Change in your
because
end
in my weight situation, what did you do?
Yeah, it's change in your end v minus
End v,
change
right?
in
So
initial v.
so v final minus v initial is
Yeah.
equal to delta v,
Yeah.
and again delta t. So in this situation, our change in position was like at time 0, like before time, like it was just held there, but at time 0, it's like still 0.
Mm-hmm.
But in change in velocity, we know that like literally like 1 second later, it becomes faster.
Right.
So that means there is some change in like there is a
Accelerate.
different like vf. So we know vi is 0,
Mm-hmm.
but vf is something. So that means there is some acceleration value.
Right.
So it's vf over delta vt. So now we need to know why there's an acceleration on this in the first place.
Sure.
So this is a big story, but the final like the summary of it is that, do you know anything about Newton and the apple?
Well, he was sitting under a tree and an apple hit him in the head.
Yeah, and
then he ran home.
no, he basically concluded that like there's. I mean, we don't know if the apple story actually happened, but
right.
He basically concluded that like all objects like fall towards Earth because there's a force pulling it down. So when you're standing, is there gravity acting on you?
Yes.
Even
Otherwise
though
I'd be floating.
Otherwise you'd be floating. Perfect. So gravity is always acting on objects on Earth, and gravity is a force.
Mm-hmm.
Again, this is from like 5 lectures later or something in physics.
Mm-hmm.
Force is equal to mass times acceleration.
Right.
So, because the mass of this object is constant and the force of gravity is the same at every point, so basically, force is equal to mass times acceleration,
Mm-hmm.
and the mass is constant, and the force is also constant, therefore,
acceleration is the variable.
But if acceleration is a variable, then force would change too.
That's true. So acceleration is a constant.
Acceleration is constant too. So some genius already.
Always? Okay, yeah.
Acceleration is constant if gravity is the force. So
okay, if gravity is the force, acceleration is constant.
Yep.
Got it.
So if gravity is the
Okay.
force, acceleration is always the same.
Well,
Which
we're not
makes-
taking into account wind resistance, though.
Yeah, we're not taking into account wind resistance. Wow,
Okay.
I'm even surprised you knew about that. That's like crazy physics. Anyways, so that gives us very crucial insight. Next, we need to know. So say we have some value of gravity.
Yeah.
In this case, since the ball is falling down, is it positive or negative? What do you think the value would be for acceleration?
Would be positive.
Why do you think
I
so?
guess if it's falling down, it would be negative.
Okay, that's reasonable. Why do you think so?
Because. But then also, if it's getting faster,
Mhm.
then it's getting faster, so it would be positive.
So
I don't know.
yeah, so no, but everything you said so far is correct, and you didn't know because this was a trick question. So acceleration is positive or negative based on what you set as your 0 point and which direction you set
Yeah,
as
the
your
direction.
right.
So I guess if it's going down, it's negative. If it's going up, it's positive.
yeah, but if you set it that way, so
Sure,
if
if
you
I
if
set
you
it up that way, but if I also set it up that this is going positive, then the other way would be negative.
yeah,
It's
so
arbitrary.
exactly. So going back to position being arbitrary, because like if you made this like -5, then the velocity would be some negative value. Similarly, the
Right.
acceleration would be some negative value,
Right.
and that's how it keeps becoming negative.
Mhm.
So in this situation, what do you want to set as the downward? Do you want it to be negative or positive?
The downward can be negative.
You want it to be negative? Okay. So a super genius physicist from a few centuries ago has discovered that the absolute value of gravity is 9.8. For simplicity in calculations, let's assume it's 10.
10.
So
Okay, so
with that information, how would you continue to fill that table?
acceleration.
Mhm.
So you said acceleration equals mass.
No, the physicist already found it for you.
Oh, so acceleration is just 10.
Is it positive or negative 10 for this ball?
Negative.
I mean, it's basically what you pick.
Uh-huh.
Okay, so if acceleration is negative 10 over there,
Uh-huh.
what would be over here?
Negative 10.
Perfect. So you know that
It's
because
negative 10 here, because some genius already found out for me.
yeah, but why is it the same
Because it's
everywhere?
constant.
Because it's constant. Awesome. So we know acceleration is negative 10,
Sure.
and we know it took 1 second for the ball to reach here.
Mm-hmm.
So we have a formula for acceleration and we have a formula for velocity. Can we find something from that? So writing acceleration.
And velocity.
I mean, yeah.
So
Okay, how would you write this in like a formula way? This sentence.
change in velocity.
Delta V over delta.
Delta t or just t?
You have the sentence right here.
Change in velocity per unit of time. So over t
Okay.
equals a. Okay.
Mm-hmm.
And do I do the same for velocity?
No, I mean, so now you have an equation with how many variables?
Oh, well, I guess it would depend on what v is right here, what the acceleration would be.
Yeah, but what other variables do you have in that equation?
Time.
Time, and you have time over here.
Sure. So I guess delta v over 1 equals 10, negative 10.
Yep.
So delta v equals negative 10.
But we aren't looking for delta V.
We're just looking for v.
We're looking for V at time equals 1. So what is that?
Negative.
So what is delta V? Remember we established that?
It's the change in position per unit of time. Delta.
No,
oh, delta
what is
v.
delta V?
Delta
Yeah.
v.
Sorry, I didn't do this right. Remember when I gave you that example about how my weight changes?
Yeah.
So in that term, what is delta V?
your end weight minus
Right.
your initial weight.
So in this case, what is delta V?
Your end
Mhm.
velocity minus your initial velocity.
So which one do you think this is? Is it end or initial?
This is, well, in relation to this,
Mhm.
it's end.
It's end. So we have two values here. Okay, so can you use that to find out what is the final velocity? So you've written delta V is equal to V final minus 0.
Sure. Like
And
this.
why did you divide it by 1?
1 second.
Oh, okay, yeah, okay. Yeah, it's equal to negative 10. All right. So V final minus 0 is equal to negative 10. And V final is equal to negative 10. Yeah, you got it. So, go ahead, fill the table. V final is equal to negative 10. Similarly, can you find the position for me?
Sure.
Let's make this easier by erasing all this stuff.
Well, I mean, we have a sentence for position, so I guess
Yep.
I can make an equation out of it and then
Yep.
follow the same.
Yep,
So
you're good at the game.
where you are with respect to a certain arbitrary plane.
That's hard. Use this one instead.
Velocity?
Yeah, use the equation of velocity to find position.
Velocity is, so it's change in position over time.
Mm-hmm.
Change in position over time. So therefore it's position final minus position I
Mm-hmm.
over time.
Mm-hmm.
And time is what we're trying to solve for.
No, actually, we know the time. We know.
Oh yeah. We're trying to find the
Yeah.
position.
So when we say per unit time, we're like
Right.
this whole action
Okay,
happened
so
between these two times.
So the position I is 0,
Mm-hmm.
and then the time is 1.
Yep.
And this is equal to position.
Is it equal to position? Position is equal to position.
Or no, that doesn't make sense. I guess it's equal to velocity.
Yep.
Yeah, velocity.
Mm-hmm.
And we already know the velocity is
Yep.
negative 10. So negative 10 equals position F.
Yep.
Minus 0, position F is negative 10.
Yeah. Mm-hmm.
And so we plug it back into well, I guess it's negative 10.
Yep.
Sure.
Right.
So,
So
I'm gonna do the same
two
thing
more.
here.
Yep. Mm-hmm.
Okay. Okay, so our velocity is equal to position F.
Mm-hmm. You can write xi or xf because position is denoted by x. I'm just saying to make it faster for you.
It's okay. Position I over time.
Yeah.
Well, we already know that time is 2.
Mm-hmm.
So velocity equals well, this is the new position I, and this is df.
Well, actually, we're taking time too, so that happened across this time span.
Oh, so we're not using it in relation to this. We're doing it from here to here.
So yeah, you use the unit time on which the whole motion occurred in. So if you're saying
Okay.
final position is this and initial position is this, then you would use 2 seconds. But if you use only these two, then you have to change the initial velocity and stuff too.
I understand then.
So
Okay,
why would you start from if you would start from position to find velocity? You can't do that really because you're missing something. So you're saying initial is 0?
Yeah, right here.
Mm-hmm. But Well, this actually doesn't work out that way because you need to first find velocity.
True.
Yeah.
You're right. So velocity is just position.
Velocity.
Yeah. Change in position per unit time.
Yeah. And that is equal to
acceleration.
Yep.
Oh, because we already found all the acceleration, so we can just use that.
Yep.
So is delta v over t. So acceleration is we know delta v is just v final minus v initial. And so acceleration. So we know that our v initial. This is our v initial, right? So that's v final, which is what we're trying to find, minus 0 over t. Well, our t is 2, and our acceleration is negative 10. So negative 20 equals v final minus 0. So v final is 20, negative 20. So we can fill that in.
Yep.
And now we can use the other formula.
Because you have the v final now.
Now we have v final, so now we can use the position one. So now our velocity equals position final minus position I over time. Well, our velocity is negative 20, and our position final we don't know, pf minus pi, which is 0, and our time is 2, so negative 40 equals pf. So it's negative 40.
Yep. Let's see how much time we have. Okay, 3 minutes. So now, can we make graphs of all the things you found?
Sure.
Because that is the ultimate way we can use to explain all this. So I have a position graph, a velocity graph, and an acceleration graph. It's time, position. Okay, so wait, let's just do that first.
Sure.
So you have the various positions at different times.
Well, we already know that our t is 1, 0, 1, or 0, 1, 2, and then our positions, it goes 0, negative 10, and negative 40.
Yep.
So we start here at 0, and then at t1 we have negative 10. So negative 10 is right here. And that's where it is right there, and then negative 40. So that's where that's our position graph, right?
But this is more like a 2. Okay, yeah, fair enough.
Yeah,
so
this is a
connect the lines. All right. So can we similarly have a velocity and acceleration graph?
Yeah. Time, and we have our velocity graph. So velocity. So 0, 1, 2, and then our velocity. Well, we have 0, negative 10, and negative 20. So so this one's more like a parabola.
Yes.
And this one's more like a.
It's more linear.
Straight line.
Yep.
And then this is our acceleration. So this is time. And this is ACC. And so it's going to stay the same because time is our independent variable. And our accelerations are constant, so they're all just going to be.
Yep.
Sure.
So you already described it. Did you notice that? Now,
That's
say if
a parabola.
Yeah. So if I was at negative 3, what do you think this value would have been?
Well,
just like guess.
so
Like, do you think
negative 80?
Probably, yeah, probably something higher than that. So while it gets to 3, it's actually increasing really fast.
Yeah.
So it's increasing in the y-axis faster than it's increasing in the x-axis.
Right. I see.
So it would like be like some sort of like some shape like this, like some curve. But in this case, they both are increasing at the same rate. So this is like a linear graph, and this one doesn't change at all.
Right. It's constant.
Yeah. So now you can use what you learned in Math 32A to explain why it's this way. What is the relationship between these 3 graphs?
Well,
it's a basic concept of Math 32A.
vectors.
Yeah, the other basic concept, or I guess like more like Math 31A.
The instantaneous rate of change.
Mm-hmm. No, exactly. So how are these related to each other that way?
Well, the position, that's, x, and then our velocity is the derivative of the position.
Right.
And then the acceleration is the double derivative of the
Right.
position, or the derivative of velocity.
Perfect. So now you experimentally showed why it is the way it is.
Right.
So I would have loved to explain energy and all that stuff, but unfortunately the time for this video is out.
Yeah.
So
Thank
thank
you,
you.
Kushal.
No problem.
I understand physics now.
I did not make him say that.